भर दिया सर पूरा, अभी भर दिया पूरा। जब
बोल काय मतदानाला जाणार आहेस की नाही तू? असं झालं का? आता चालेल की लिस्ट मध्ये नाव येईल. ठीक आहे, काय करायचं म्हटलं? काय करायचं, काय करावं लागेल?
मी घेतलेली सॉफ्टवेअर इंजिनिअरिंग हा मी घेतली होती सॉफ्टवेअर, पण त्यांनी एक प्रोसिजर पाठवली डीएस कोडची.
ओटीटी का फुल फॉर्म क्या है? ओटीटी प्लेटफॉर्म कहते हैं ना इसका फुल फॉर्म क्या है? ओवर द टॉप। गजब है ना।
What's it called?
Hello?
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 My
My
sound.
sound is vibrating.
Hello?
Hello?
Ma'am, your voice
Hello,
is echoing.
Ah,
my
I
I am
am
somewhere else also.
My
Voice
is
is
echoing.
echoing.
Now?
Now?
Now it is
There
okay.
are seen?
Yeah, now it is okay, ma'am.
Okay. So speaker join.
Yeah, sir is there.
Good morning, ma'am.
Okay, so we'll wait 5 minutes.
Ma'am, can you hear my voice?
Yeah, you have joined.
Yes, ma'am. I joined, ma'am.
Okay, your name is not reflecting.
Oh, it is
Ma'am,
not
it's
reflecting
visible.
here.
It's visible. It's visible here.
There, ma'am.
Dr. Ranjith Gowda, it's visible.
Okay, okay. Okay.
Yes, ma'am.
So just 2 minutes we will wait. People are joining. Gerard sir,
Yeah,
you write in a group, WhatsApp
I have
group.
put already. Please join like that. I have
Everybody.
put.
Yeah.
Ah.
Then you can start. People may join. slowly. Hello, Ranjit. Hello.
Yes, ma'am.
Yeah,
Can you hear, ma'am?
I can hear you. Your photo is not visible.
Actually, in my laptop camera is not there, ma'am. Otherwise, I will now I will turn on in my phone, ma'am. 1 minute.
Okay. Few photographs we will take. That's why. Yeah,
Yes,
now
ma'am.
very clear. You are in college?
This is through. Yeah, I'm in college,
Okay.
ma'am.
Okay. So Jairaj sir, take photograph.
I'm taking one.
Okay. So now we will start in formal way by giving introduction. And if you are comfortable by switch off the photograph, you can. Okay.
Yeah, that is. It is because here less bandwidth is available, ma'am, in our college.
Okay. No issue.
So that's better.
No issue. So please start, Jairaj.
A very good morning to one and all present here. On behalf of the President of Children's Education Society and Chairman of the Oxford Educational Institutions, Management, Principal, Deans, HODs, staff and students of the Oxford College of Engineering, I welcome you all for the 7th day of 2 weeks International FDP on Advancement in Quantum Computing and Sensor Technology for Vikshit Bharat at 2047, organized by departments of CSE, ISE, ECE and EEE. On this occasion, it's my great pleasure and honor to welcome our chief guest, Dr. Ranjith B. Gowda, Government CPC Polytechnic, Mysuru. Dr. Ranjith B. Gowda received his MTech in VLS and Embedded Systems from BVB College of Engineering, Hubli in the year 2018 and PhD in Optical Sensors for Biomedical Applications from Dayanand Sagar University, Bangalore in the year 2023. Currently, he is working as a senior lecturer in the Department of Electronics and Communication Engineering, Government CPC Polytechnic, Mysuru. He has teaching and research experience of more than 15 years and has published many research papers in reputed journals including SCI, SCIE, ESI, Scopus Indexed, and peer-reviewed journals and conferences. He is a reviewer for many reputed journals. He is the author and editor for technical books published by international publishers. His areas of interest include optical sensors, DBR, MEMS, NEMS, microfluidic devices, and microstructures for biomedical applications. He holds various memberships such as Institute of Electrical and Electronics Engineers, IEEE India, Institution of Electronics and Telecommunication Engineers, IETE India, Indian Society for Technical Education, IST India. He has contributed a book chapter titled Distributed Bragg Reflector Biosensor for Medical Applications in the book Computational Health Informatics for Biomedical Applications in the year 2023. I welcome you, sir, and I request you to kindly take over the session.
Thank you, sir. Thank you for the introduction. First of all, I would like to thank Dr. Pritashan ma'am for giving me an opportunity to share my knowledge in this workshop. With this, first of all, I would like to say good morning to all the participants. Shall I share the screen, sir?
Yes, sir, you can share.
Is my screen visible, sir?
It's visible, sir. You can put it in presentation mode.
Yeah. Okay. Good morning, everyone. So in the today's presentation, the topic of my session is optical sensing using a distributed Bragg reflector. And these are the contents of today's session. First, we'll be having what is photonics, why photonics is required, photonic crystals, Maxwell's equations, different types of photonic crystals, distributed Bragg reflector. This is another one type of photonic crystal, and one case study I have taken, and then conclude. First, what do you mean by photonics? In simple way, I can say photonics is the study of light. It is a physical science of light, we can say. It deals with the science behind the generation, detection, and manipulation of the light. There is a difference between the optics and photonics, where the optics is a broad area which includes subtopics like physical optics, geometrical optics, quantum optics, etc. In case of geometrical optics, mainly we are interested with the ray property of the light. There we are going to consider the light will behave as a ray. in case of geometrical optics, especially when we use the light beam in the lenses. Cases, we will approximate the light as a ray, and we usually call this as geometric optics, or sometimes it is also called as the classical optics. Whereas in case of physical optics, we will consider the nature of the light. For example, in case of holographic images, I can say, where the diffraction and interference will come into picture. There we consider the light will behave as a wave. Where we have as a two properties, light and the light can behave as a particle. There when as the particular study of the light by considering light as a particle, we call this as the quantum optics. Quantum optics and photonics, they are very closer actually. In quantum optics, we are more interested with the theoretical aspects, whereas in the photonics, we are more interested with the physical applications of this light wave. And as I told, light has a dual nature. The light can behave as wave, and the light can behave as a particle. Here we are interested with the quantum optics. In quantum optics, we will consider the light will behave as a particle. We know it is called as a photon. And wave nature of the light is operative. It depends on the what type of applications and what kind of observations we are going to do. And in particularly in today's life, photonics refers to the creation, manipulation, and the detection of the light for the various applications. Next, why photonics is required? Why we are more interested with the photonics? So we know the light can travel in a dielectric medium with higher speed as compared to the electrons through the metal wire. And the light can carry larger amount of information per speed, which means that the bandwidth of the dielectric material, obviously it is very high. More information we can easily transmit through the proper channel. And light particles or the photons are not as strongly interacting as the electrons, which helps in reducing the energy loss. So there we can avoid the energy consumptions, unwanted energy consumption we can avoid. And there is no electromagnetic effect, easy generation of the light with the lightweight sources, low power consumptions. And these are some of the advantages of using photonics for the physical applications. Now coming to the photonic crystals. Photonic crystals are periodically structured dielectric materials where the dielectric is varied in different directions. And PHCs are initially invented by John and Ebenovich in the year 1987, and they act as crystals for the photons. They will guide the light through them. And photonic crystals are said to be the optical analog of the semiconductors. And photonic band structure is equivalent to the electronic band structure where we can observe in case of semiconductors. And in PHCs, in the photonic crystals, the periodic potential is due to the lattice of macroscopic dielectric media instead of the atoms that we can observe in case of semiconductors. We can observe valence band, conduction band in case of semiconductors. Similarly, here we are going to observe photonic band gap. We call this as the PBG. So PBG is one of the important property of the photonic crystal, by which, using which we can study the various property of the light, propagation of the light, reflection of the light, absorption of the light through the material. And PBG is a range of frequency wherein which the particular frequency of the light is prohibited, which will not be allowed to propagate through the crystal. So we call this as the photonic band gap. And by creating a defect or by changing the periodicity of a photonic crystal, it is possible to make one particular beam of light, one particular frequency of the light to propagate in the PBG region. That is possible. So we call this as the defect engineering. That is a broad area. In the defect engineer, we are going to study the different types of defects that we can able to create, and what are the various types of applications wherein which we can use these types of photonic crystals. That and all we are going to study in the defect engineering. And the basic equations, we know Maxwell's equations for the electromagnetic waves. These are the four master equations we call del dot D, del dot B, del cross E, and del cross H. And after some calculations and the simplification, we obtained the master equation. And this last equation is actually called as a master equation for the photonic crystals. And in this master equation, what we can observe is epsilon r, that is the nothing but the relative permittivity of the material, how it is related to the frequency. Omega is the angular frequency, and epsilon r is the relative permittivity, and they are related so that if epsilon r value changes, then definitely the propagating frequency or the wavelength we can able to manipulate, using which we can able to use these photonic crystals for the various applications. And we know the relationship between the refractive index and permittivity. Epsilon is equal to n square, and a change in the refractive index definitely changes epsilon, and change in the epsilon definitely changes the frequency of the light propagating through the structure, and hence it can be used for the it can be used as a sensors for the various applications. Coming to the different types of photonic crystals, three main types we can observe: 1D photonic crystals, 2D, and 3-dimensional photonic crystals. In case of 1-dimensional photonic crystals, there is a variation in the refractive index in only one direction, for example, in only x direction, as shown in the figure. Whereas in case of 2-dimensional photonic crystals, the change in the dielectric constant is in two direction, or change in the refractive index is in two directions. Whereas in case of 3D, in all the directions, in all the three directions, the refractive index is changing. So particularly here in this session, we are interested with one type of 1D photonic crystal. We call this as the distributed Bragg reflector. So distributed Bragg reflectors are the examples of one-dimensional photonic crystals. And distributed Bragg reflectors, they are composed of repeated pairs of high and low refractive index material. High and low, high, low, high, low. It will repeat in one particular direction. And this is the best example for the one-dimensional photonic crystal. And film thickness is usually chosen as optical quarter wavelength, lambda by 4. This should be the thickness of the material. It is a material we are going to, dielectric material we are going to consider while fabricating the DBR. And larger refractive index contrast and higher number of pairs can lead to the higher reflectivity. More reflectivity we are going to get, that we will see in the next slide. And here in this equation, the reflectivity equation we call, this reflectivity depends on the different parameters like NH, NL, Na, and Nb. Here NH is the refractive index of the high material. High material I mean to say this material is having higher refractive index. Whereas NL is the refractive index of the low material. Low material actually means that one material which is having low refractive index. And gamma is the reflectivity of the light. And change in the refractive index, either NH or NL, will change the reflectivity gamma. So by using this property of the photonic crystal, it is possible to change the reflectivity gamma. Now we will be having one particular example for the DBR, where I will consider this dielectric mirror. Here we can observe that two layers are there which are repeating in x direction. In some direction it is, in one direction it is repeating. The first layer is the NH layer, which means that this is the higher refractive index layer, and the second layer is the lower refractive index layer. Again it is repeating higher, lower, higher, lower, higher, lower, like that it is repeating. So how many such pairs are there is called as N. N is the number of pairs of materials we have used here. One high material and one low material, which forms one pair. We call here N is equal to 4. For example, if N is equal to 4, it means that there are 4 pairs of the material. One high refractive index material, another low refractive index material we are using in this particular type of sensor. In this example, particularly, I have taken higher refractive index material as the TiO2, titanium dioxide, which is having the refractive index of 2.4, and the low refractive index material I have considered here as a SiO2, silicon dioxide, with the refractive index of 1.46. And these two refractive index of the material TiO2 and SiO2 are true at the optical wavelength of 10.6 micrometer. This is very important because the refractive index of the material will change with the propagating light. So here these two are the refractive index of the material at the wavelength of 10.6 micrometer at this wavelength. And the small LH and the small LL is the geometrical length of the higher and lower refractive index material. Here small geometry, there is a difference between the geometrical length and the optical length. Geometrical length here means this is the actual length. When we fabricate the DBR, what is the actual length of the material, high refractive index and low refractive index material. This is called as the geometrical length. Then what is optical length? How to get optical length? To get optical length, geometrical length should be multiplied with the refractive index of the material. For example, I want to have the optical length of the higher refractive index material. For example, OH. O is the optical length and H is for the higher refractive. Then I have to multiply LH with NH. If I multiply small NH with small LH, then that will give the optical length. So this is the difference between the geometrical length and the optical length. And the rho is called as the reflection coefficient, and we can able to calculate the reflection coefficient using the equations shown in the slides. NH minus NL divided by NH plus NL, or reverse also we can able to take, so that we will going to get minus rho, NL minus NH divided by NL plus NH. And refractive index contrast, as I said in the previous slide, this we can able to calculate using the equation NH minus NL divided by NH, where NH is the higher refractive index material and NL is the lower refractive index material. So if the RIC is more, then the reflectivity is more. More the RIC, more the refractive index contrast, then the reflectivity will also be the more. And coming to this dielectric mirror response, so we can observe in this graph that in the x-axis I have shown lambda, which is the wavelength of the light, and in the y-axis I have shown the reflection of the light. And here I have taken in the x-axis, the wavelength will vary from 300 nanometer to 800 nanometer, whereas in the y-axis, so this is the reflection of the light from 0 to 100. This is in terms of percentage. So in this case here we are having three different graphs. We have obtained three different graphs. This is for the different values of n. As I already told that n is the total number of layers we are going to use in the distributed Bragg reflector, total number of layers. For example, here if I consider n is equal to 2 and n is equal to 4 and n is equal to 8. So three different n values I have considered here in this case. We can observe the reflectivity of the light, that if n is equal to 2, dotted line is the response what we are going to get, and if n is equal to 4, that is the dashed line we are going to get, that is the response. And if n is equal to 8, that has been shown in the continuous line. So these are the three different responses we have got, that is the mirror response, dielectric mirror response, reflection of the light. And we have considered the wavelength range from 300 nanometer to 800 nanometer. This is the wavelength range we have considered here. And what we can observe in this particular slide is, suppose if the number of layers increases, suppose if I take n is some range of more the number of layers, then the more the response the response becomes more flat. So that is what we can consider here. And if for n is equal to 2, we can observe that the reflection is not look good, and for n is equal to 4, it's okay. Whereas for if I take n is equal to 8 or more than 8, then the response is very flat. So clear response we are going to get. And what is the difference from left edge to right edge that we can observe here? It is about some 420 to 620. For example, I can say some 420 nanometer to 620 nanometer. If I say the difference is actually called as the difference in the lambda, and this is called as PBG, photonic band gap. We call this as the photonic band gap. And what is the center frequency I have chosen in order to get this type of response is lambda naught, that has been shown that it is equal to 500 nanometer. It is the center frequency we call. This 420 to 620, what actually it means? All the light, if it is having in the range of 420 to 620, that will not be propagated through the photonic crystal. It will be reflected. It will coming back to the source side instead of going back to the destination side. So this is called as the reflection. And suppose, so in the earlier case, for the previous structure, we have seen what is the dielectric mirror response. Now what I will do in the second case is I will introduce one defect cavity. So here we can observe in this diagram that we are having low layer, high layer, low, high. It will be repeating like this. And after 4 pairs, after n is equal to 4, after first n is equal to 4, we can observe that now after NH, I will be having NL, but again NL is coming. So here we have altered the periodicity of the structure, or the periodicity of the sensor we have altered. So this is called as the defect cavity. So it is not necessary that we have to introduce defect as only low layer. We can introduce any other defect. We can introduce high refractive index material, or we can introduce some other material. I have taken TiO2 and SiO2 as the high and low refractive index material. But for the defect, I can take ZNO. That is possible. Or the zinc selenide, ZNS I can take, zinc selenide. That is the defective material. So that I will introduce in between these two. So in either side, we can observe n is equal to 4, whereas in the middle, we will be having another layer that is called as the low layer. So this will change the periodicity of the structure. So because of that, what will happen? If there is no defect, then dotted line is the response. We can observe the dotted line. So, and here the y-axis is the transmittance. Instead of reflection, now I have taken the transmittance. And if I observe the dotted line, I can say that the frequency, the wavelength range from 1400 nanometer to almost 1800 nanometer. With respect to dotted line, I'm talking. With respect to this, almost 1800, there is no propagation of the light. So this is called as the PBG here. But with the introduction of defect, if I introduce NL, then we can observe the reflection of the light like this. It means that at one particular wavelength, lambda naught, there is a transmission. Instead of reflection, there is a transmission of the light. 100% transmission we can observe here in the continuous line. That is possible with the help of with the introduction of the defect cavity. Here in terms of equation, I can say L. L is the low material that I have added here. And in either side, I am having 6 pairs. Here in this example, I have taken 4 pairs. Suppose if I take 6 pairs instead of 4 pairs, then this is the response we are going to get. From this, we can conclude that if I alter the periodicity of the material or the periodicity of the DBR, then I can able to use this as a sensor. In the defect, if I put some sample, for example, some blood sample or pressure, if I put pressure on this, then definitely the refractive index of the material will change. And if the refractive index changes, that there is a shift in the wavelength. This transmission graph we can observe, and this transmission graph will start shifting. That we will study in this particular case study. Here in this case study, I have taken the detection of oral cancerous cells using highly sensitive one-dimensional DBR Fabry-Perot microcavity. Here we have created one cavity at the middle, and this behaves as a Fabry-Perot microcavity. So here in this particular example, I have taken the high refractive index material as the germanium and the low refractive index material as the zinc selenide at the wavelength of 10.6 micrometer again, which is in the near infrared range frequency. And germanium acts as high refractive index material. This 4 and 2.19 for the zinc selenide. These two are true at the wavelength of 10.6 micrometer. And this is the proposed design. Here we can observe some base material we have used silicon, and above that we have created the Bragg reflector, DBR. In this case, we have considered n is equal to 6. The blue color material is the germanium material, and orange color material is the zinc sulfide. And this is the base material we have considered with n is equal to 6. And light has been propagated from one side, and it can be observed in the another side. And the transmission spectrum obtained for the such type of structure we can observe here. So this is the transmission spectrum for the previous structure. Here we can observe that the wavelength range from around 9.2 to almost 10.4 or 10.6, I can say. This is the PBG region, photonic band gap region, we say. It means that the wavelength, the wavelength from 9.2 or 4 micrometer to up to 12.2 or 4 micrometer, this range of light will not propagate through the earlier structure what I have shown. And this is called as the photonic band gap region. Now, to make one particular light beam to propagate through the structure, what we should do, for the earlier structure, we have to introduce one cavity. In this diagram, we can observe that in the left side, we are having n is equal to 3, and in the right side, we are having n is equal to 3. So 3 pairs I have added, and in the middle, I have created one cavity. So this is having some length. I will call this as the LD. LD is the defect cavity length, actually it means. So one cavity is introduced here. What is the advantage of using such type of cavity is, now if the cavity is introduced in the PBG region, as I have shown in the previous slide, in the PBG region, one particular light will start propagating through in the PBG range of frequency or in that particular wavelength. And here in the structure, what I have shown here, we have considered the two waveguide. One waveguide is used to transmit the light. That is this waveguide, light input and light output is there. This particular waveguide is used to transmission of the light. Whereas the another waveguide we have used, where we are going to put the sample, analyte we can able to put. So here, what is the analyte? That is the saliva we consider, because we are detecting the oral cancerous cells. So saliva we can put here. And suppose if I consider this saliva, it contains both normal and cancerous cells. Then how I can able to detect it? By passing the light through this waveguide, and when the analyte will come into this particular position, there is an interaction between the light and the matter, and I'm going to get the transmission spectrum. And somehow I will get some transmission spectrum. By observing the transmission spectrum, I can able to decide whether this saliva contains the normal cells and this saliva contains the cancerous cells, or only normal cells, or both normal as well as the cancerous cells, that we can able to detect. And this is the transmission spectra that we have obtained with no analyte. If nothing is introduced in the defect cavity, if the cavity is empty, if it is filled with the air, if nothing is there, then this is the transmission spectra obtained. Now we can observe that in the PBG region, this is very important. In the PBG region, one particular wavelength is start transmitting, and almost 58 to 60% of transmission we are obtaining if the cavity is empty. And if you observe the wavelength, we call this as the resonant wavelength. And if I observe this resonant wavelength value, this will be exactly equal to 10.6 micrometer. What is the 10.6 micrometer? This is the incident light wave we have considered. That is the input light. Input light we have chosen 10.6 micrometer. Why 10.6 micrometer? Because we have chosen two materials, germanium and zinc selenide. This particular material will be having some refractive index 4 and 2.19 at the wavelength of 10.6 micrometer. So that is the reason why I have considered 10.6 micrometer. And another advantage of considering this mid-infrared frequency is, in this particular frequency range, the sensitivity of the structure is high, low absorption we can able to observe. So these are the another advantages, other advantages we are having by choosing the this infrared mid infrared range frequencies. And these are the some of the parameters we have taken from particular reference paper, which was the experimental paper from the Optics Express, which was published in the year 2010. And there in the experiment, they have given that the normal cells and the cancerous cells, they have studied 5 normal cells and 5 cancerous cells, oral cancerous cells. And normal cells are called as INOK here, and the cancerous cells are called as YD10B, one type of cancerous cells it is. And for the 5 cells, they have considered what is the change in the refractive index in the cells. For the cell 1, if it is the normal cell, then its refractive index value is 1.343, whereas if it is cancerous, then it is said to be 1.369 for the first cell. Similarly, for the second cell, third cell, for the fifth cell, it is 1.351 normal, and for the cancerous, it is 1.378. By observing these values, by observing the refractive index of the normal cells and by observing the refractive index of the cancerous cells, we can say that the refractive index of the normal cell is a little bit lower as compared to the refractive index of the cancerous cells. And in the another reference paper, in the literature study, we came to know that why the refractive index of the cancerous cells is more. It is because of the more protein concentration. They have given that for the cancerous cells, protein concentration will start increasing. Once the cells turns into cancerous cells from the normal cells, the protein concentration of the cell will increase. And that is one of the reason for increasing the refractive index of the cancerous cells. So here the maximum value for the normal cells is 1.351 in the 5 cells. Out of 5 cells, maximum refractive index for the cell 5, it is 1.351, whereas for the cancerous cells, the minimum refractive index for the cell 1 they have taken as 1.369. They have studied this is the refractive index of the cancerous cells, and highest it reached up to 1.378 out of these 5 cells. And these are the cells that we have considered in our study. We have taken these 5 normal cells and 5 cancerous cells, and we have done this simulation. We have studied this structure, and this is the transmission spectra obtained. Here, the transmission spectra obtained, we can observe that continuous lines are there, 5 continuous lines, and 5 dotted lines are there. So these continuous lines, from the legend, we can observe this is for the normal cell, INOK1 to INOK5, 5 normal cells we are having. This is the response, and 5 cancerous cells that is represented in the dotted line. So what we can observe from this continuous line and the dotted line is, in the continuous line, we can observe that cell 1 is having lower refractive index as compared to the cell 5 of normal cell 5. So as the refractive index of the cells increases, then we can say that the resonant frequency or the resonant wavelength starts shifting towards the right side. This is the shift that we can observe. And if I consider the cancerous cells, we in the earlier table we came to know that the cancerous cells are having higher refractive index as compared to the normal cells, and shifting the wavelength we can observe continuous red line and dotted red line. So this will be having the resonant frequency of about 11.28, for example, and this will be having the resonant frequency of about some 11.34. This is the shift. So as the refractive index increases, then the shift in the wavelength also we can able to observe here. And suppose if I put unknown sample, so what is the conclusion from this is, for the normal cells, suppose if I put some unknown sample in the defect cavity, and if the sample contains only the normal cells, then definitely the resonant wavelength will be in the range of 11.26 to 11.32 in this continuous line region. Definitely it will lies in this region. Whereas if it contains cancerous cells also, then definitely the resonant wavelength will lies from 11.32 to 11.4. So in this range, in this particular range, the resonant frequency will lie. I can divide this plot vertically into 2 parts. Left side is the normal and right side is the cancer. By considering 11.32 as the demarcation point here, I can say left side is the normal and right side is the cancer. In this particular region, the resonant wavelength will lie. So from this reference, we can, if I put unknown sample, then I can definitely say whether this sample contains only normal cell or it contains cancerous cells also. Then we have studied the defect of increasing the defect length. Initially, we have set some defect cavity length. Let it be, for example, 0.5 micrometer. That was the initial length of the cavity. At the middle, what is the defect cavity we have created? That's its length is 0.5 micrometer. Then we have observed, suppose if we change the defect cavity length, what is the change in the resonant wavelength? And then we are going to observe what is the change in the sensitivity of the sensor. So here in the left side graph, I have shown for the fifth cell, INOK5 and cancerous fifth cell. And we have observed that as the defect length increases, then the resonant wavelength will also increase. We have changed the defect cavity length from 0.5 micrometer to 4 micrometer. And in the same way, the resonant wavelength will also start increasing, and it reaches up to 12.8 micrometer. This is the shift in the resonant wavelength. From this, we have observed the sensitivity of the sensor. So suppose if I vary the defect cavity length 5 micrometer to 4 micrometer, what is the change in the sensitivity? We have plotted this graph, right side graph. It shows the graph between the dependency of sensitivity on the defect cavity length. So as the defect cavity length increases, then the sensitivity will increase. Beyond that, the sensitivity will not increase. That we have studied, but it is not shown in the graph. In the another paper, we have actually shown after this experiment, we have shown this. And after certain, once it reaches certain value of defect cavity length, suppose if I increase more than that, either the sensitivity will reduce or the transmission will reduce. So based on that, we have to take, particularly we have to set what is the actual defect cavity length that we have to choose, so that we have to get the intended parameters, intended sensitivity we should get, intended quality factor we should get. Based on that, we have to set the defect cavity length. And here, as the defect cavity length increases, we can say that the sensitivity of the sensor will also increases up to certain range. Then we have studied what is the effect of increasing the number of layers. Initially, I have shown there are 4 layers on the left side and 4 layers on the right side, and in the middle, we are having the defect cavity. Suppose if I, instead of 4 layers, suppose if I take 6 layers, if I take 10 layers, then what will happen? That we want to study here. So we have varied the number of layers from 3 to 6. We have taken only 3 to 6. Initially, we have taken n is equal to 3, and it has been changed to 4, 5, and 6. And we have observed what is the change in the transmission spectrum. As we can see in the left side graph, here x-axis is the wavelength in micrometer, and y-axis is the transmission. If n is equal to 3, we can observe the green color graph plot. And if I increase the value of n, and if I reach n is equal to 6, then blue color graph we can observe. So this becomes very narrow now. So as the number of layers increases, then the quality factor will start increase. Means the resonant wavelength will becomes very narrow instead of wide. Very narrow resonant wavelength we are going to get. And what is the effect on the transmission? We can observe if I increase the value of n, then the transmission starts reducing, but it is very little bit in this case. In this particular case, it is little bit. Whereas in the other case, other experiment, there we have observed that even for the small change in the value of n, the transmission will start very quickly. From 80 to it becomes 60, 60 to it becomes 20, 20 to it becomes 0. Even for a smaller change in the value of n. That is for the different case, for the other types of material and some other center frequency we have chosen. That also we have studied in the other papers. And here in this particular case, even though I have increased the value of n from 3 to 6, the reduction in the transmission is very less. It is almost in from 1 to 1 or 2% reduction in the transmission spectrum. And then we have calculated the quality factor by changing the number of, and we if I change from n is equal to 3 to n equal to 6, what is the increase in the quality factor? The quality factor will reach on quality factor that we can observe from see that the change in the quality factor is very high. And but for the practical applications, it is not suggested because the complexity will also increase. And another thing is because of the superficial roughness of the adjacent material, there is a possibility that there is a more reduction in the transmission. That is also there. So properly we have to choose what should be the value of n, so that we should achieve better sensitivity as well as the quality factor for the design sense. And these are the parameters of the sensors we have calculated: sensitivity, signal to noise ratio, detection limit, sensor resolution, figure of merit, and the quality factor. Here we are more concentrated with the sensitivity of the sensor, and which is calculated using the shown equation, and quality factor we have calculated in this particular study. And this table shows the various results that we have obtained in this particular study. For 5 normal and 5 cancerous cells, we have calculated the various parameters of the optical sensor, important parameters: sensitivity, SNR, DL, SR, FOM, and quality factor. All these we have calculated, and these are the results that we have obtained. And then finally, what we have done, we have chosen n is equal to 6 and LD is equal to 4 micrometer. As I have shown in the earlier slide, if I make LD, defect cavity length, as 4 micrometer, then the sensitivity will reach to the higher value. And if I take n is equal to 6, then the quality factor will reach us to the higher value. For the final design, we have optimized the structure by taking n is equal to 6 and the defect cavity length as 5 micrometer, and we have obtained the sensitivity as 3630 nanometer per RIU and the quality factor as 11,323. These are the satisfied value, very high value we have obtained for the design sensors. And then we have compared the proposed sensor with that of the recently published work. Actually, this work was published in the year 2021. And we have taken, at that time, we have taken the recent references 2019 and 2020 papers, and we have shown that the sensitivity, here we are concentrating more on the sensitivity of the sensor rather quality factor, and we have obtained 3630 nanometer per RIU. This is the that is the sensitivity of the proposed sensor. And in summary, one-dimensional multi-layer photonic crystal structure DBR we have proposed with the 6 pairs on either side of the defect cavity to detect both the normal as well as the cancerous cells. And by optimizing the structure, by making the n is equal to value of n is equal to 6 layers on either side, and a defect cavity length of 4 micrometer, we have obtained a very high sensitivity of 3630 nanometer per RIU with a quality factor of 11,323. And this paper was published in the elsewhere optic journal in the year 2021. Thank you. Thank you, everyone.
Participants, if you have any queries, please unmute yourself and you can ask.
If you have any queries, you are free to ask.
Participants, any queries, please, you can unmute yourself and ask. I think no queries are there.
No queries are there. Yes, sir.
So I'll give the formal vote of thanks. On behalf of the management, principal, deans, HOD staffs, and students of the Oxford College of Engineering, I thank Dr. Ranjith Gowda for his excellent talk. I think all our participants were very much benefited by your talk, sir. Thank you very much.
Thank you, sir. So I thank everyone, especially Dr. Preeta Sharan ma'am and principal, HOD of E&C department and all the management of TOCE for giving me an opportunity to share a few knowledge in this particular workshop. Thank you, sir. Thank you, everyone.
Thank you, sir. Thank you.